Alkanones and Alkanals. We now have another functional group, the carbonyl group. The carbonyl group is a functional group that is found in most biological molecules, pharmaceutical agents, and many synthetic chemicals which touch our daily lives. Some examples: citric acid in lemon and oranges, acetaminophen, brand name Tylenol, Dacron, the polyester fabric. This one consists of a carbon double bonded, there's the double bond there, to an oxygen. The dash on the left side of the group shows that it bonds to another molecule. The location of a carbonyl group in a molecule determines its functionality. The types of molecules containing carbonyl groups are bulleted below. The sub-bullets, these are the sub-bullets here, show the subset of that group that also contains at least one alkyl group. We'll be studying the subgroups. So you have ketone as the main group, and we're going to be talking about alkanones, which have a carbonyl group and at least one alkyl group. Same thing, we'll be talking about alkanals, subset of aldehydes, then alkanoic acid, subset of this, and finally alkanoates, subset of esters. Ketones are compounds which have at least one carbonyl group between two carbons in a molecule. This is written as R-CO-R'. CO is a carbonyl group, and that's this guy here. R is any group of atoms with at least one carbon. R' is also any group of atoms with at least one carbon. R and R' can be the same or different, and R and R' can be chains or cyclic structures. But we're going to focus on alkanones. They're a type of ketone in which both R and R' are alkyl groups. That also means they cannot be cyclic. Right? Here's an example here. A cyclic, you'd have to be making a circle. The alkyl groups can be the same or different, but they both have to be alkyl groups. In the following case, two ethyl groups are connected to a carbonyl group to form acetone, which is the alkanone. And we have various different pictures here. And in both cases, the R's are CH3. And see how we write it H3C here? That shows that the carbons are bonding together. And this is another way of notating it. So this, we're assuming there's a carbon there. And what do we have to do? We have to make 3 more bonds because every carbon has 4 bonds. So that's where the H's come in. And here's a ball and stick diagram, shows the same thing. So what do we have here? H is white, okay? The C's are here. And then oxygen is this guy over here, and you can see, hopefully you can see the double bond there. 3 different ways of representing this formula. Let's talk about naming alkanones. Here's the functional group again, which we just showed a slide or 2 ago. That's carbonyl. It is usually sandwiched between 2 alkyl groups. So let's start with the alkane, propane in this case, which has the formula CH3, CH2, CH3. When the central CH2, and hopefully you can see that's somewhat of a lighter blue, is replaced by a carbonyl group, which is CO, it will be CH3, CO, CH3. And there's our carbonyl group, again in a slightly lighter blue. That molecule now is called propanone. Its name is formed by dropping E of the respected alkane, which is propane, and adding 1. It also has the common name acetone. And that's the problem with all this organic chem. Sometimes you have multiple names for the same thing. Similarly, this is butane, and this one will be butanone, replacing CH2 with the CO. Its common name is methyl ethyl ketone, or MEK. We derive the alkanones from the alkanes. Here's our alkanones. Here's the alkane. By replacing a CH2 group with a carbonyl group, CO. So we go down here. Our anes are CnH2n plus 2. So we take away 2 hydrogens. So that'll just become H2n. And then we take away a carbon, but then we put the carbon right back. Okay, you can see there's a carbon there. And there's a carbon here also. So let's look at propane. C3H8. So we remove a carbon, but we put it right back with the hydroxyl molecule. So the carbons stay the same. We take away 2 hydrogens, so we get H8 goes down to H6, and then we add an O, and there you go, C3H6O, and that is propanone. So what do we have here? 1, 2, 3, 4, 5, 6 examples. And here's an exercise for you. Please complete the table for the next 4 alkanes and alkanones, heptane, octane, nonane, and decane. So pause the video and restart it when you're ready to check the answers on the next slide. Let's start with decane, and that's going to have 10 carbons. So the formula here says C10, and then how many H's will you have? Well, 2 times 10 is 20, plus 2, 22. Okay, now to go over to decanone, take away a carbon, but it comes right back with the hydroxyl. So we'll just write C10 again. We take away 2 hydrogens, right? Because we took away the CH2. So let's see, 22 goes down to 20. So H20. And then we add the oxygen. So right there. So please review the other ones and move on when you're ready. Let's pause for a second and give a great example of the very tremendous importance of the functional group. A small change in a molecule, one functional group, can make a big change in its function. Exchanging a hydroxyl group for a carbonyl group changes estrogen, which is the hormone for female creatures here, it's a lioness, to testosterone, which is the hormone that creates males, like this male lion. Let's move on to our next group here. We have aldehydes. Those are compounds which have at least one CHO group present in the compound. It consists of a carbonyl group, which we've studied, and a hydrogen atom over here. The general formula for an aldehyde is R-CHO. In this case, R can be a simple alkyl group or a complex cyclic or aromatic, which we will discuss later in an advanced level course. But let's look for this thing here for aldehydes. Alkanals, which we'll talk more about now, are a type of aldehyde in which the R is an alkyl group. The CHO attaches to the terminal carbon, that's the last carbon of an alkyl group. In the following case, one methyl group, CH3, that's over here, is bonded to a carbon in the CHO group to form acetaldehyde, an alkanal. Here's its formula. Here's its structure over here, where we have a hot carbon here, and then we have to put 3 more hydrogens, so it has 4 bonds. There we go. And here's the double bonded oxygen, and what's over here? Well, that's a carbon also. The ball and stick diagram, these are great. You can really get a good sense of what the molecule looks like. Here's our hydrogens, the white spheres, carbon's gray, and here's our doubly bonded oxygen. Naming alkanals. The functional group is CHO with a double bond between the carbon and the oxygen. Each CHO, carbon, hydrogen, oxygen, will replace a methyl group in an alkane. Then for naming, drop E of the parent alkane and add al. For example, methane has the formula CH4. Replace the methyl group, CH3, with CHO to obtain HCHO, which is methanal, whose common name is formaldehyde. Ethane has the formula C2H6. Replace the CH3 with CHO to obtain CH3CHO, which is ethanal, which has a common name of acetaldehyde. The alkanals are derived from alkanes by replacing a methyl group over here with an aldehyde group. Okay, so the general formula for alkanes is CnH2n plus 2. So let's see how we get the general formula for an alkanal. Well, we take away a CH3. So Cn goes to Cn minus 1. And since we take away 3 H's, instead of 2n plus 2, we have to take 3 away from that 2. 2 minus 3, negative 1. So we have 2n minus 1, and then we add the CHO at the end. We add the aldehyde group. Exercise time. Complete the table for the next 4 alkanals, and then check your answers on the next slide. So we'll work one of them. This time we'll do octane. Okay, so that's CN, so we have 8, right? Octopus, 8 arms, oct means 8. Then hydrogen, 2 times 8 plus 2. 2 times 8 is 16, plus 2 is 18. Then octanal, Cn minus 1, so 8 minus 1, 7. 2n minus 1, 2 times 8 is 16, minus 1, we get 15, and then we add the CHO group. Physical properties of alkanals and alkanones. The boiling points of alkanals and alkanones are lower than the alkanol with the same number of carbons because alkanols are polar and have hydrogen bonding. Alkanals and alkanones with less than 5 carbons can have their oxygen atom bond with the hydrogen atom in the water molecule with a hydrogen bond. These lower members, such as ethanol and propanone, are soluble in water. Those with higher numbers of carbons are insoluble in water due to the large hydrocarbon chain which resists hydrogen bonding. Those with fewer carbons are liquids and are less dense than water and ethanol, so they'll float on top of them. Many alkanals and alkanones have a characteristic, strong, some would say pungent smell. Now caution, follow lab protocol for smelling chemicals. Only with instructor's permission. Waft the odor. Do not directly inhale. That means use your hand to blow the odor to your nose. Don't put your nose over the bottle. Some uses. Ethanol, which is this molecule here, is used for silvering glass to make mirrors. It is also used for preparing acetic acid, which is vinegar, butanol, and ethyl acetate. Ethanol is used in dye manufacturing. Methanol, or formaldehyde, is used as formalin for preserving biological specimens. Octanol is found in both orange oil and juice. It is also used in perfumes and food preparations. These ketones and aldehydes are found in nature. Iron, here's a cinnamon flavor, raspberry, here's vanillin, here's benzaldehyde. And all of them have pungent smells. Some of these at least are nice, right? Cinnamon, raspberry. Uses of ketones and aldehydes. Acetone, and here's where it has a pungent odor and it is not good for you to smell, right? Nail polish remover, as a solvent in laboratory synthesis, as a solvent for celluloid and nitrocellulose, for the preparation of chloroform and iodoform, and this will knock you out, that chemical there. Various alkanals and alkanones are present in flowers, fruits, and beans and are responsible for their odors and flavor.